Today I would like to talk about counting permutations and combinations. So please turn in your study guide to this section. Now let's begin with the counting principle. Before we go into the properties of probabilities and odds, we need to understand the counting principle. We use the counting principle to determine how many different ways an event can occur. It's easier to define the fundamental principle of counting through examples. So I'd like to take a look at some examples here to define the counting principle, and let's begin with example 1. Now in example 1, it says Fred is deciding on an outfit to wear for a charity event. He has a choice of 2 different sports coats, 7 ties, 3 pairs of slacks, and 2 different pairs of shoes. How many outfits can Fred put together from these choices? Now, since choosing a sport coat doesn't affect the amount of choices of ties, slacks, or pairs of shoes, these events are called independent events. The choice of one is not going to change the result of choosing another. So these events are what we call independent. Now, since the events are independent, we'll just multiply the total number of each one of those stages there. And in the first stage, he's going to pick a sport coat. There's 2 choices for that. Then he's going to have a choice of 7 different ties. And then in our third stage, we have a choice of 3 pairs of slacks. And in the fourth stage, we have a choice of 2 different pairs of shoes. So if we multiply 2 times 7 times 3 times 2, Fred can make a total of 84 different outfits made up of these 4 different stages. So there are 84 possible combinations to form his outfit. And the principle we used here is the fundamental principle of counting. And once again, we did recall that our stages each were independent from one another, so we simply multiplied the total number of each of the stages and their possible outcomes to get the total number of outfits, in this case, that Fred could wear. Now let's take a look at example 2 here. Sue, Terry, Stacy, and Janet are runners on the mile relay team. How many different arrangements can this team run if each runner only runs one leg of the race? Now, this is a little bit different than our previous example. Unlike the independent example earlier, when we designate a girl to run the first leg of the relay, that eliminates one runner from the remaining choices of runners. Therefore, these events are referred to as dependent events. So once I make a selection in one particular stage, it's going to lower the number of remaining possibilities for my other stages as well. And that wasn't the case earlier when we talked about Fred's outfits. Picking a certain sport coat didn't affect the number of ties that he had to choose from. However, in this case, with the relay runners, once we assign one individual that first leg of the race, we cannot assign them any other positions in that race itself. So these events are referred to as dependent events. So at first we have 4 different choices of runners to run the first leg of the relay. So our first number in the multiplication problem will be 4. Now that one runner has finished, the number of runners to choose from in the second leg of the relay is reduced to 3. Next, it's down to 2. And finally, it'll be down to the last runner that has not been assigned. So the problem will be 4 times 3 times 2 times 1, or 24. There are 24 possible ways we can arrange these runners to run this mile relay. Once again, we took a look at this example as being an example with dependent events, and so it did change the way we multiplied. Now in the previous example, we saw that there were 4 times 3 times 2 times 1, or 24 ways to run this relay. However, there's a symbol for this very idea. An exclamation mark represents the term factorial. So, for example, 4 factorial is equal to 4 times 3 times 2 times 1, or 24. Factorials are very useful in statistics and probability. Therefore, the problem can be written simply as 4 factorial, which ends up being equal to 24.